Welcome to a session on Maxwell-Boltzmann distribution of molecular velocities. In this session, we will be seeing an expression for Maxwell-Boltzmann distribution of molecular velocities and also the effect of temperature on distribution of molecular velocities. Let us move on to the topic. So, here the two topics we will be dealing in the session is Maxwell-Boltzmann distribution of molecular velocities. We will get an expression for that we will be explaining the effect of temperature on molecular velocities. Now, we all know that in gases the molecules are in a rapid random motion in which they will be colliding with each other and also with the walls of the container. Though the collisions are elastic, what happens here is during collisions their velocities get altered and as a result their kinetic energies also get altered. Now, what happens is you will be having, that is, a molecule starting with a particular velocity. After collision it may change its velocity. So, you will be having molecules in a gas with very low velocity values and also very high velocity values, okay, and there will be most of the molecules having a common velocity. Now, how these molecular velocities are distributed is explained using an equation known as Maxwell-Boltzmann distribution law. Okay. Now, this is how the molecules velocity, that is individual molecular speeds, are distributed over a broad range at a given temperature. That is what we are going to analyze. Maxwell and Boltzmann have shown that the distribution of gas molecules over a range of possible velocities from 0 to very high, that is the maximum value possible at that particular temperature, depends upon molecular mass of the gas and temperature. Now, just for clarity's sake, we can see that if the molecular mass is high, naturally the molecule will be moving about with lower velocity. And the vice versa, if the molecular mass is less, it can move more freely, so they will be having high velocities. So, that is the case of molar mass. Now, when we come to the temperature, when temperature is high, its kinetic energy of the molecules will be high, and if kinetic energy is high, they will be moving with a high velocity. When temperature is low, kinetic energy will be low, automatically the velocity will also be low. So, these are the main two factors that determines the velocity of the molecule. Once the mass is increased, the velocity is lowered. If the temperature is increased, velocity is increased because they have high energy and they can move fast. And they have developed an equation, the derivation not required, which is like dN by N, okay, is equal to 4 pi into m, which is a molecular mass, divided by 2 pi RT whole raised to 3 by 2 into e to the power minus mc square divided by 2 RT. That is all. Next comes multiplied by c square dc. Now, I will explain the terms. What is dN? dN is the fraction of the molecules which possess a velocity in the range c and c plus dc. That is here, it is the number of molecules out of total number of n molecules which possess velocities between c and c plus dc. That is, c is the velocity, a slight increase dc in that. So, in that range of velocity, what is the number of molecules out of total molecules? That is written as dn. N, now it is clear, it is a total number of molecules, and this term dn by n. Now, what will be that? Dn is the number of molecules having velocities between c and c plus dc, and capital N is the total number of molecules. Okay. So, out of total number of molecules, dn molecules possess velocities between c and dc. Now, this is considered as fraction of the total number of molecules that possess a velocity between c and c plus dc. Okay. Now, here m is the molecular mass of the gas, T is the Kelvin temperature, capital R, as you all know, it is a universal gas constant. Universal gas constant. T is absolute temperature, E is the exponential term. Again, here also we have m the molecular mass, though the velocities between c and c plus dc is considered. We consider for calculations, we will take c as the velocity. So, c square and dc, that is a small change in velocity. Now, what I am going to do is, I am going to take this dc to the left hand side. Okay. So, we will have the term 1 by n, this n is taken out because dn dc will go together. So, 1 by n, okay, that is I am taking dc to this side, it is in the numerator, it goes to the denominator. So, actually it will be dn by dc comes to the denominator, capital N is there, is equal to 4 pi m by 2 pi RT whole raised to 3 by 2 into e to the power minus mc square by 2 RT into c square. Now, just rearranging that, taking out 1 by n, dn by dc is equal to 4 pi m by 2 pi RT whole raised to 3 by 2 e to the power minus mc square by 2 RT into c square, dc goes to the other side. Now, here dn by n is the fraction of the total number of molecules having velocities between c and c plus dc at an absolute temperature capital T. Okay. But here now the fraction has been changed as 1 by n dn by dc, and this represents the probability. Okay. The term 1 by n dn by dc, that is the term here, the above equation represents the probability of finding the molecules having a velocity c. So, this represents probability, the other thing is fraction of the total number of molecules. Now, one more point to be remembered is, you can find out the effect of temperature by taking either considering the fraction of total number of molecules, that is dn by n, or you can take the probability, that is 1 by n dn by dc. Now, let us see what is the effect of temperature on molecular velocities. Maxwell distribution of molecular velocities is represented by plots on y axis the fraction of number of molecules or the probability of finding the molecules having velocities indicated on the x axis. Okay. Now, here comes a plot for Maxwell distribution of speeds of hydrogen molecule. The distribution according to Maxwell distribution law of speeds for hydrogen molecule is shown in this graph. You can see the fraction of the molecules on the y axis and velocities on the x axis. Just watch the shape of the curves obtained. The first one, blue one, is at 25 Kelvin. The second one is at 50 Kelvin. And the third one, that is a green one, is at 300 Kelvin. Okay. Now, let us go through the changes observed here. In first case, that is at 25 Kelvin, you can see there is a steep, very big peak. It is the tallest peak. Next one is some more lower one. The third one is highly lowered. Now, this represents the fraction of the molecules possessing this maximum. This is a maximum value of velocity at 25 Kelvin for a particular molecule, for the particular molecule. I am going to label this velocity as V1. Okay. Now, when the temperature is 50 Kelvin, just see the fraction of the molecules. It has been lowered, but the velocity value, if you check, it is a higher one, V2. Now, again going to 300 Kelvin, the velocity value is again increased to V2, but you just check the fraction, it is very low. So, this is the fraction of the molecules possessing the highest velocity. Now, you can see that when the temperature has been increased from lower temperature to higher temperature, there is a shift of these peaks towards the right hand side. Right hand side means that is in the direction of increase in velocities. So, naturally the velocity V3, which is at 300 Kelvin, is greater than velocity V2, which is at 50 Kelvin, which is greater than V1, which is at 25 Kelvin. So, these are the velocity values. So, as the temperature is increasing, the velocities are naturally increasing. And when we check the fraction, it has been seen that fraction of molecules possessing the highest velocity is being lowered as the temperature is increased, or you can say that the curves have been broadened with the peak flattened. That is what has happened here. So, these are the observations we get depending on Maxwell's distribution of molecular velocities, and that is for hydrogen gas. Now, let us go for the plot at two temperatures. That is, here we are having the probability is 1 by n dn by dc. Okay. So, the probability is plotted against velocities. You can see that here we are taking only two temperatures, T1 and T2, no numerical values, of which T2 temperature is greater than T1. And here is the velocity that is increasing in this direction. Now, again we are having two peaks here and the corresponding probabilities here. The probability of this one for the maximum velocity is here. So, you can see it has been lowered. Now, when we watch these two plots, we can see some of the observations, like the probability of a molecule remains stationary at any instant is extremely small. Probability of a molecule to remain stationary. Now, here this is when stationary in the sense it is fixed, it is not moving, or you can consider where the velocity is equal to 0. See the probability, it is almost 0. That is, molecules to remain stationary in a gaseous phase, it is not possible. So, they will be moving. Now, second is the fraction of the molecules having very low velocities and very high velocities. Fraction of the molecules having very low velocities and very high velocities. Now, these are the very low velocity values, these are the very high velocity values, and their fraction is also very small. So, molecules to remain stationary, it is impossible because you do not have any probability factor over there. For lower velocities and very high velocities, again the number of molecules that possess very low and very high velocities are very low. So, that is another observation. Next is the peak of distribution curve at a given temperature gives the velocity possessed by maximum number of gas molecules at that temperature. See, that is the peak of the curve. Okay, this is showing the velocity, okay, possessed by maximum number of molecules, because the peak is at the peak, it is the topmost portion where we have the maximum number of molecules, and that velocity is the peak. Here we have these two. Okay. Now, the velocity possessed by maximum number of molecules at a temperature is known as most probable velocity, or denoted by the Greek alphabet alpha. So, again I will repeat, the velocity possessed by maximum number of molecules at a given temperature is known as most probable velocity. So, these are the most probable velocities, maximum number of molecules. Okay. These are the most probable velocities, that is alpha and alpha. This is at the temperature T1, this is at the temperature T2. So, these are the most probable velocities. Now, the total area under the curve, when you take a curve, okay, the whole area underneath it is a measure of total number of molecules, that gives us a measure of total number of molecules. The area under the curve in the velocity range, we are going to take a range C1 and C2, which I have not marked, I will do it now, represents the number of molecules having velocities between C1 and C2. So, I am going to choose two velocities C1 and C2. The area under the curve in this region gives us the number of molecules that possess the velocities between C1 and C2. Now, let me mark it on this graph. So, I am going to take the velocities from here. I will rub that in order to avoid any confusions. Let this go. Okay. So, I am taking this velocity as C1 and another velocity here, let that be C2. So, for the first curve, so this is for the temperature T1, the number of molecules in this area, let me color it in yellow color. Okay. These are the number of molecules when the temperature is T1. So, this area represents the number of molecules which possess the velocity between C1 and C2. This is the color I have given is yellow, that is when the temperature is T1. Okay. Now, what I am going to do is, I am going to extend this to the second curve which I have maintained at T2, that is a different temperature higher than T1. Now, the area under the curve means it will start from here till the base of this x axis. So, I will color it with another different color. I will take, okay, I will take green. See, that is, it starts from here, it will start from here and it should meet the curve. So, this is the area where we have the temperature. I forgot to mark it, I have done it like lines, green colored lines, okay. That is for temperature T2 and the velocity is the same C1 to C2. Okay. Now, just watch this. Area under the curve is giving you the number of molecules possessing velocities between C1 and C2, and you can see that when temperature is increased from T1 to T2, what is happening to that? When it was T1, see, only this much molecule possessed the velocity between C1 and C2. When I increase the temperature to T2, just find the great increase, huge increase in the value of the velocity possessed by molecules under the curve between C1 and C2 velocities. So, when temperature is increased, there is an enormous increase in the velocities of the molecule. So, more molecules come for that higher velocity values. Now, we will go back. The total area under the curve is a measure of total number of molecules. The area under the curve is the velocity range between C1 and C2, represents the number of molecules having velocities between C1 and C2. Hope it is clear. Now, with increase in temperature, it is seen that the distribution curve broadens. Let us see the distribution curve. This is the distribution curve. This is somewhat steep. The other one with a higher temperature, it has widened or broadened. So, that is correct. Now, second point is it shifts to the right. It shifts to the right means it is shifting towards higher velocity. See, at T1, at T2 it has been shifted to right where the velocities are of higher value. So, the plot is shifting towards the right, towards higher velocity. That is the second point. Third one is it gets flattened downward at the top. Now, here just watch, here this was at this high, when the temperature is increased, it has got flattened. That is, the fraction of molecules possessing the maximum velocity, or the name is most probable velocity, has been decreased. Okay. Now, this is because there occurs a rise in fraction of the molecules having higher molecular velocities. That is the reason we have the broadening of the curves. Then the most probable velocity alpha increases, the value of velocity increases, that is shifting towards right. So, this is the velocity in one case. At higher temperature you have this one, and it is very clear at higher temperature the value of velocity is higher than the previous one. Okay. Now, fraction of the molecules possessing the actual most probable velocity decreases. Fraction of the molecules that possesses most probable velocity. See, these are the most probable velocity values, and this is when temperature is T1 and this is when temperature is T2. You can see that it has been flattened, which means that the value of probability value of molecules having highest value has been decreased, and that is represented by the flattening of the peak. Now, to conclude, we have been seeing Maxwell-Boltzmann distribution of molecular velocities, and we have been seeing the effect of temperature on molecular velocities. The Maxwell-Boltzmann distribution of molecular velocities is represented as 1 by n dn by dc is equal to 4 pi into m by 2 pi RT whole raised to 3 by 2 into e to the power minus mc square by 2 RT into c square. Okay. Now, when we explain the effect of temperature on molecular velocities, the points to be noted is the probability of a molecule which remains stationary, these are the points, it is very low. Then molecules possessing very low velocity and very high velocities, they are also very low, very small. Now, peak of the distribution curve gives a velocity possessed by maximum number of molecules, which is known as alpha or most probable velocity. And the definition is velocity possessed by maximum number of molecules at a particular temperature is known as most probable velocity, denoted by the Greek alphabet alpha. The total area under the curve is a measure of total number of molecules possessing that particular velocity range, and it has been seen that the area under the curve C1 to C2, that is the range of velocity, it represents the number of molecules having velocities between C1 and C2, which we have shown in the graph. Okay. Now, when temperature is increased, the distribution curve broadens, one point. Second point, it shifts towards the right. Third point is it is getting flattened downwards, and from that we get the observations like these occurs as a rise of fraction of molecules having higher velocities with increase in temperature. The most probable velocity increases with rise in temperature, and fraction of the molecules possessing the actual most probable velocity decreases, that is by the flattening of the curve. Now, this can be explained in terms of Maxwell-Boltzmann's equation, in which you can see the temperature factor. Where is it? It is in the exponential term e to the power minus mc square divided by 2 RT. So, this is the term. Now, this is multiplied by e to the power. So, we will see all these, they do not change much, only the temperature is changing. Now, this temperature being in the denominator of a negative exponential, what will happen when T increases? What will happen to this fraction? We will leave the negative sign. When T increases, the numerical value of this term increases, that is excluding the negative sign. But we know that, suppose I am taking 10 to the power 2 minus 2, 10 to the power minus 3. These are the negative exponents. Now, when the numerical value is increasing, see from 2 to minus 3, the value is decreasing, right? The value is decreasing. So, here when T increases, which is in the denominator, the whole value, the numerical value, when T increases, the whole numerical value decreases. That means there is an increase in the value of this term, and that is in the exponential terms, like from minus 3 to minus 2. It is in terms of exponential, and therefore, when there is an increase in temperature, the fraction of the molecules possessing a particular velocity, there is an exponential increase in their velocities. So, that is all for this session. Thank you.